The objective of this analysis is to estimate the settlement of a circular water-filled tank. The tank is 10 meters in diameter and 4 meters high. It has a completely flexible base, and the applied pressure on the ground when the tank is full is 40 kPa. Since the problem is symmetrical about the vertical center line of the tank, the problem definition will only include half of the tank, and an axisymmetric analysis will be conducted. Once GeoStudio has been opened, a new Sigma analysis can be created from the Start page by selecting an analysis, creating a new project, or using the File drop-down menu. The first time you start working with Sigma, it is helpful to learn what different toolbars exist. In Sigma, many of the drop-down commands are also available as individual icons on the many different toolbars. You can familiarize yourself with the toolbars by toggling them on and off, ensuring that they are all visible before you start the analysis. When developing a numerical model, the first step is usually to set the working area, which defines the size of the space available for defining the problem. The working area may be smaller, equal to, or greater than the printer page. The next step is to set the scale. The scale should be set such that the minimum and maximum extents in Sigma match those required for the analysis. You can define either the X and Y minimum and maximum extents to get an idea of an appropriate scale, and then fine-tune the scale to have a 1-to-1 aspect ratio. A background grid of points will help you draw the problem. These points can be snapped to when creating the problem geometry. The problem definition data must be saved in a file. The data may be saved at any time during a problem definition session. It's a good idea to save the data frequently. All Sigma files have a GSZ file name extension. It's often helpful to sketch an axis. Before you start, click the Zoom page icon so you can view the entire working area. Then choose Axis from the Sketch menu. The axis is drawn by moving the cursor to the bottom left corner, clicking the left mouse button, and then stretching the axis until the necessary size has been achieved. Next, prepare a sketch of the problem dimensions. Choose Lines from the Sketch menu, and use the cursor like a pencil, clicking the left mouse button to create a series of lines that outline the problem geometry. Clicking the right mouse button will exit the Sketch Lines mode, and additional lines can be drawn by using the pull-down menu again or by clicking on the Sketch Lines icon in the toolbar. Text can be added to the profile by using Sketch Text. Type the text you would like to see and format it as you desire. Then use the cursor to place the text on the profile. Once the problem has been sketched, some information about the analysis to be conducted should be defined. Choose Analysis Settings from the Key-in menu. Any appropriate text can be typed under the Project ID tab. Click on the Control tab and select the Axisymmetric option. Click on the Type tab to make sure a Load Deformation Analysis type is selected. A linear elastic total stress analysis will be performed on this example problem. Define the materials using Key-in Material Properties. Highlight the default material in the list box and select Linear Elastic from the drop-down list. Then define the material properties for material number 1. Click the Copy button to write these values to the list box. Then define the parameters for the second material. Remember to click Copy to accept these values. Click the OK button to exit the dialog box. It's a good idea to save the simulation frequently. Click the Zoom Objects icon to maximize your view of the drawing. For this problem, the finite element mesh will be generated using 4 regions. 8 noded elements will only be used under the tank, while 4 noded elements will be used for the rest of the mesh. The number of nodes in your finite element mesh will affect both the size of your file and the amount of time required to solve the file, so it's prudent to only use secondary nodes when necessary. To draw the regions, choose Regions from the Draw menu. The cursor will change to a crosshair. Move the cursor over the sketched lines and click the left mouse button to create region points. A finite element mesh will be automatically generated. In the Region Properties dialog box, click on the Mesh tab to ensure that quadrilateral elements are being used. Click on the Elements tab and select the Secondary Nodes option. Then click on the Edge tab to fine-tune the number of elements on an edge. Select Edge 2-3 and type 10 in the minimum edit box. Use the Copy button to confirm this change. Once the dialog box has been closed, your cursor will still be a crosshair, so you can continue to define additional regions. Notice that you can modify the number of elements on an edge by either clicking on the edge directly with your mouse or by selecting the edge in the subdivision list box. Change the material assigned to a region by using the drop-down menu on the Material tab. When you're done, exit Draw Regions by right-clicking the mouse button. You can alter the information shown on the finite element mesh by choosing View Preferences. Turn off the point labels, region numbers, and element numbers, and change the font size of the node numbers to be 4. The next step is to apply boundary conditions. In Sigma, boundary conditions can be specified at nodes as displacement, force, or spring stiffness. Pressure boundary conditions, such as those applied by the water tank, are applied to element edges. Choose Edge Boundary Conditions from the Draw menu. Use the Zoom button to highlight the nodes that exist under the tank and select Normal Tangential Stress from the drop-down menu. Type 40 in the Normal Edit box, representing a pressure of 40 kPa. A positive value indicates a compressive stress. Use the mouse to drag a box around the element edges at the bottom of the tank and release the mouse button. Blue arrows indicate that a normal force is being applied, and a thick blue line is displayed indicating that the pressure exists along the edge of the elements. Zoom out to view the entire problem again. Choose Node Boundary Conditions from the Draw menu. Along the left vertical boundary, the soil cannot move in the x direction but is free to settle in the y direction. Select X displacement under the boundary type and leave the action as the default value of 0. You can apply the boundary condition to individual nodes, or you can use the mouse to select several at a time. Along the bottom of the mesh and down the right vertical face, the displacement will be 0 in both the x and y directions. Set these boundary conditions and apply them to the appropriate nodes using the mouse. You can create a table of material properties using dynamic sketch text. Choose Text from the Sketch menu. Click on Insert Field. Select the material property information you would like included in the table, and in the Material List box, expand the drop-down list and select All Materials. Select the checkbox beside Show as a Table, and then click Insert. Find an appropriate location on the profile, and use the mouse to place the table. We've finished the problem definition, and now it's time to verify the analysis. Click on the Verify button. Sigma will run a number of checks. The solver for Sigma can be launched by clicking on the Solve icon. Click the Start button to activate the solver. You can view the results directly by clicking on the Contour icon in the Analysis toolbar. By default, the deformed mesh will be displayed on the profile. Since it isn't necessary to view node numbers or elements, use View Preferences to turn these off. Also, select the shading checkbox and ensure material color is selected. One of the main objectives of this simulation was to determine the settlement of the water-filled tank. To view the maximum deformation, choose Displacement from the Draw menu. The maximum displacement calculated by Sigma was 76 millimeters. In the profile, all the displacements have been magnified 23 times, and you can increase or decrease this value for presentation purposes. You can also look at the stress distributions that have developed beneath the tank by drawing contours. It's important to note that for this analysis, the contours are the stress changes as a result of the tank load. They are not the total stresses in the ground. To view the total stress in the ground, it would be necessary to first conduct an in situ analysis to determine the initial stresses and then add the tank to determine the total stress. Choose Contours from the Draw menu. Select Y total stress from the drop-down list. Change the default values to have the contours start at a value of 5 kPa and increase in increments of 5 up to a maximum value of 35 kPa. Click in the box beside Contour Shading. In order to view the contours more clearly, you can turn off some of the contour information using the View Preferences icons. Each contour interval is shaded a different color. Choose Contour Labels from the Draw menu. Click on each contour to create a label and re-click on the label to turn it off. Click the right mouse button to finish labeling contours. Another way to view the results is to create a More Circle. Choose More Circles from the Draw menu. Move the cursor and select either a node or a Gauss region where you would like to know more information about the stress results. A More Circle window will appear showing the stresses for that node or element Gauss region. Click the right mouse button to exit. You can view results at specific locations by using the View Node and View Element Information commands. Choose Node Information from the View menu. Click on a node to see the results that were computed for that node. You can resize the dialog box to view all the information. The only information that has been actually computed at the nodes is the deformation and boundary forces. Stress and strain values were actually computed at the Gauss regions and then projected to the nodes for displaced purposes. To see the actual computed results at the Gauss regions, select Element Information from the View menu. The Element Information box can be resized in the same way as the Node Information box. You can create a number of different graphs to further investigate the results obtained from the analysis. Choose Graph from the Draw menu. Select X displacement from the first drop-down list box. Select Y coordinate from the second drop-down list, and use the mouse pointer to select a vertical group of nodes at the right edge of the tank, which will be used to generate the graph. You can view the graph directly, or you can copy the raw data into a spreadsheet for further analysis. At any time, if you want to go back to define, you can click on the pencil icon in the Analysis toolbar. You can also return to the GeoStudio Start page by clicking on the Start page icon. On the Start page, you have access to some important resource material. You can then return to the current analysis by clicking on the appropriate icon. We have reached the end of this introductory lesson. Not all of the powerful features of Sigma have been used or discussed during the lesson. Specific details about each command are given in the online help and in the supporting documentation for Sigma.